Right, I think we can start now. So welcome to the second problem solving session of the fundamental algorithms course. So week one quiz deadline is probably tomorrow. So I hope that all of you have solved week one questions. And I think that the session that we conducted last time was helpful for you. So in this session, we will look at some practice problems of week two. In fact, these are the questions that were posed in the previous run of this course. So the idea is if you solve these questions, this will help you in solving week two quiz questions this time also. So I will let you read the first question. So this is the first question. So today we are changing gears slightly and we are looking at hash tables and hash functions. So I'll let you read the question. So we have a hash table of size 7. Okay. And indexing starts at 0. And the hash function is the following. So it takes x and outputs 3x plus 4 mod 7. Okay. Assuming the hash table is initially empty, which of the following is the contents of the table when the sequence 1, 3, 8, 10 is inserted into the table using closed hashing? So the important thing is this closed hashing. So note that this symbol denotes an empty location in the table. Okay. So first let's draw a schematic diagram of the hash table. So let us say the hash table looks like this. It has 7 slots. It is empty initially. And the numbers that we want to insert are the following: 1, 3, 8, and 10. Okay. The question is, after we have inserted these 4 numbers, what is the hash table going to look like? Okay. So let's look at 1. So first we are going to insert 1. So we are going to apply the hash function on 1 to identify the slot in which 1 should be populated. So 3 into 1, instead of x, I'm writing 1 plus 4, entire thing mod 7. So that is equivalent to 7 mod 7, which is equivalent to 0 mod 7. That is 0. Okay. So in the 0th index, so indexing starts at 0. So at the 0th index, we should put 1. We'll do that. So 1 is inserted at the 0th index. Is that fine? Similarly, we are going to insert 3, 8, and 10. And if there are conflicts, that means if 2 numbers are mapped to the same slot by the hash function, then we are going to use close hashing technique to resolve collisions. Okay. So can one of you do the calculation for inserting 3? So where should 3 be inserted? In which slot in this hash table? A simple calculation. So I'll give you a minute to identify where 3 should be inserted using this hash function. Six, Ravi is saying at 6. Okay. Okay. Anybody else? Well, let's do the calculation. So it's very easy. So instead of x, we are going to write 3. So 3 into 3 is 9. 9 plus 4. 9 plus 4 is how much? 13. 13 mod 7. So that is 6. So it's correct. Let's write it. So we will do 6 mod 7. So 6 is empty, so we can write 3 here. Okay. Now how about 8? Where should 8 go? Position 1. That means here. Okay. Let's look at it. So 3 into 8 plus 4 mod 7. That is equivalent to, so 24 plus 4, 28 mod 7. That is 28 is divisible by 7. So 0 mod 7. That is 0. So we have a conflict. So the hash function is saying that, okay, you try to put 8 here, the 0th index of the hash table, but 0th index is already occupied by 1. So what shall we do? We used closed hashing. Okay. So what do you do here? So in closed hashing, we're going to look at the next available empty slot. So in this case, the next empty slot is at 1. So 0 is followed by 1. So here we have an empty slot. So we are going to insert 8 here. Is that fine? Okay. So let's look at the position of 10. So 10 should go where? Somebody can quickly tell me. Position 2. Okay, let's do the calculation. So 3 into 10, 30. 30 plus 4, 34. So equivalent to 34 mod 7, which is equivalent to, so 6. Okay. Because if you divide 34 by 7, the remainder you get is 6, right? But 6 position is already occupied. We already have 3 here. So what shall we do? So we have to find the next available position, but next there is nothing. So it will wrap around. We'll check here. We'll wrap around, we check here. We say that, okay, again, there is something here. So we keep on moving in the forward direction. Again, there is something. So we find the first empty slot here, position 2. Okay. So here we are going to insert 10. So this wrapping around is important. So we bring 10 here. So after inserting these 4 elements, this is the state of the hash table. Okay, this is what we are asked in the question, that when the sequence 1, 3, 8, and 10 are inserted, is inserted into the table using closed hashing, what are the contents of the table? So what is the answer? This is the answer. So if there are any doubts on this, please ask me. I'll be happy to answer. Okay, then I think we can move on to the next question. Again, there's a question on hash tables. So I'll let you read the question. So please read the question and tell me what is the answer. So the answer is A. That's what Ravi is saying. How about others? Okay, let me explain the question first. So there is a hash table with 25 slots. If we do indexing from 0, then hash table looks something like this. The last slot is the 25th slot. Okay, 25 slots in this table. But you want to you want to store 2000 elements here. Then what is the load factor? Alpha for this table T. So how do you even store so many elements in a 25 slot hash table? That is the first question. So there is definitely going to be collisions, right? So if you have even 26 elements, even one element more than the number of slots, then you are going to face collision definitely. So what shall we do? So there is something called chaining, which is a collision handling technique. Here, what they do is the elements that are mapped to the same slot, they form a linked list. Okay, let's do one thing. We'll draw the linked list uh, horizontally. So let us say multiple elements are uh, let us say multiple elements are mapped to this ith slot. Then all these elements which are mapped to this ith slot using the hash function, they will form a linked list. Okay. So basically, when you are looking for a particular element, then you will first come to the head of the linked list and then do a traversal of the linked list to find the particular element. So on an average, the expected size of the linked list will be number of elements by the number of slots. How much is that? That is 80. So that is also called the load factor. So number of elements by the number of available slots. Okay. So therefore 80 is the answer. So I think we are going quite fast. I think you can slow me down if you have any questions. Do you understand what is going on? If there are any questions at any point, please feel free to stop me. Okay. So this is the end of second question. We will move to the third one. If you don't have questions. Okay, let's move on. Again, it's a question on hash functions. I'll let you read the question. That question. So 3 statements are given to you and you have to identify the true statements. So multiple statements could be true. So let's read the first one. A hash function takes a message of arbitrary length and generates a fixed length code. Second one, a hash function takes a message of fixed length and generates a code of variable length. Third one, A hash function may give the same hash value for distinct messages. So basically collisions can happen. That's what it is saying. Option C is definitely correct. I mean, do you mean option C or statement 3? So Ravi is saying, okay, so Ravi is saying that this option is correct. So both 1 and 3, these two statements are true. So first of all, this is easy to handle. The hash function may give the same hash value for different messages. So basically collisions can happen. So this is saying that if f is the hash function, then it can happen that it takes a message x1 and gives y as the hash value, takes another message x2 and gives the same value, and therefore x1 and x2 are mapped to the same slot, which we have seen in the previous question. So this is perfectly possible. So 3 is correct. So now we have to, so definitely option A is false, option D is false. We have to decide between these two. So how about 2 and 1? That is the question. So if you look at the hash function, it has to generate something which is consistent or uniform. So therefore the output should be uniform, irrespective of what is the size or shape of the input. And therefore generating a fixed length code is important. Okay. But the message could be arbitrary. There is no restriction on the message to be of fixed length. So this is not correct. This is correct. Okay. So therefore option 1 and I mean statement 1 and statement 3 are correct. So this 1 and 3 are correct is encapsulated in option C. Therefore, this is the correct answer. Is that fine? I'll let you uh, think about it for a moment, and then we can move on to the next one if you don't have questions. So I think you're watching the videos, then hash function and related topics are covered in the videos. You'll have more familiarity with the questions if you have watched the videos already. This is the fourth question. I'll let you read the question. So consider a hash function that distributes keys uniformly. Okay. The hash table size is 20. Let's draw the hash table size 20 hash table. After hashing of how many keys will the probability that any new key hashed collides with an existing one exceed 0.5? So it's a question where probability and hash function hashing are involved. So you have to meditate on these numbers, that the size of the table and the probability threshold that you are looking at, which is 0.5. Okay. And the fact that the hash function distributes the keys uniformly. Options are a bit confusing. That's what Ravi is saying. Why is that? Oh, for the last question. So for the last question, you had some doubts. So is it not clear that why statement 1 and statement 3 are correct? So why do you think it is not clear? Okay, 2 is confusing. So okay, so you're saying that the statement is confusing. So the statement is simple in the sense that it takes fixed length messages, let us say 64-bit messages, and generates a variable length code. Okay, so basically, there is no reason why the message should be fixed length. That is the reason we roll it up. But we would be happy to see fixed length hashed values. That is the reason we picked this. Is that fine? Okay, great. Now we'll spend some time on this question. So there's a hash function that distributes keys uniformly. So you take some x1 and x1 goes somewhere. So for every x, there is a equal probability of this x to be hashed to any of these 20 slots. So the probability that a given x goes to, or rather I would say gets slot I is 1 by 20 for all I in this set. So we'll start, let us say, start from 0. We'll start 0. So for each of the slots in the hash table, the probability that a given element x is mapped to one of these slots is equal 1 by 20. So that is the meaning of keys, that the hash function distributing keys uniformly. Now your question is following that how many keys after hashing of how many keys means after how many uh, elements you have inserted into the hash table, you would have a more than 50% or rather greater than equal to 0.5 probability of getting a collision. So once you have, let us say you have inserted, let us say k elements into the table, let us say in distinct slots, then the probability that the k plus 1th element collides with an existing element is how much? That's what we have to check. So we want to, this is our event. We want to ask what is the probability that this event occurs. So k elements are already, let us say, into the table, push in the table at distinct slots. Now we are inserting the k plus 1th element. So k slots are already occupied. K of them are occupied. And 20 minus k of them are empty. So now there is a collision. If this k plus 1th element happens to be mapped to one of the k occupied slots. Okay. There are k possibilities in which a collision can happen out of the 20 slots. So this is the probability. Is it right? So after k elements are inserted into distinct slots. So let us say k is less than 20 assumption. So then the k plus 1th element collides with an existing element is k by 20. The probability of that event is k by 20 because we have the hash function distributing keys uniformly. So that every slot there is an equal chance of the k plus 1th element to be mapped to. So this number has to be at least 0.5. So this number will equate it to 0.5, that is half. Okay. So that will give us the value of k to be how much? So that means after you have already got 10 elements inserted, then onwards, your probability that any new key hashed collides with an existing key is at least 0.5. This is our answer. Option D. Is that fine? Okay, fine. Thanks. So Ravi has got it. Anybody has doubts? Anything? So we'll move on to the next one. I think we are going to finish early today. And see we're able to understand things quickly. A good sign. So I'll let you read the 5th question. So generally after 5th question we take breaks, but I think we can take a break later. Or maybe within 1 hour we'll finish. So the 10th question is going to be the trickiest. So the last question of the session is going to be the trickiest, and you will have many interesting things to learn, hopefully, from the last question. So please read this question. This is the 5th question. Yeah, so this is a factual question that whether you either you know or you don't know. So which of the following schemes uses a randomization approach? There are a couple of hashing schemes given to you. Which of them uses the randomized approach? So if you have watched the videos, then you would have come across each of these hashing schemes. Since this is a factual question, so it's nothing to argue. So if you know the answer, you can let me know. So the answer is option C, universal hashing. Okay. So let's move to the next one. So I will let you read the question. This is the sixth question of today's session. How many distinct binary search trees can be created out of 4 distinct keys? So what is a binary search tree? The binary search tree has a property which is called the BST property. So what does this say? This says that if you look at any node, then in the left subtree of this node, you have numbers. Let us say uh, all elements or all keys are distinct. That is the assumption. Then if you have a number x in a node, then in its left subtree, all the nodes are strictly less than x. And in the right subtree, whatever nodes you have, each node has value strictly greater than x. Okay. So now you have 4 distinct keys. Let us say the keys are 1, 2, 3, 4. Then how many distinct binary search trees will be possible? That is the question. So how about starting with 3 keys? Let us say you have 3 keys. Then what is the answer? So you can draw it by hand. In fact, with some effort, in a few minutes, you will be able to draw all the possible distinct binary search trees out of 4 distinct keys. So I'll give you a minute or two. Think about it. No, it's not binary tree. It's not labeled binary tree. So for example, let me draw a binary tree. For example, let us say 1 is there. And if I have 5 as a child of 1, that violates the binary search tree property because 5 is greater than 1, right? So this is not a binary search tree. This is not equal to a binary search tree. Although it's a tree, it's a binary tree for sure because it has at most 2 children. So this is the root. This is not a BST. For it to become a BST, 1 should be to the right of it. Then this is a BST. Or if you have 5 and 1 to the left of it, that is also a BST. But 5 and 1 to the right of it is not a BST. So being binary tree alone is not sufficient. What is a binary tree? A tree where each node has at most 2 children. No children is okay, 1 child is okay, 2 children is okay, but 3 children is not okay. That is a binary tree. Now, additionally, if the binary search tree property is also satisfied at every node, then what we have is called a binary search tree. Now consider, let us say you have two keys only. So with 1 and 2, how many binary search trees can you produce? Let us say you have 1 and 2 only. And you want to ask that, okay, if I want to draw binary search trees with 2 keys only, then yes, you are right. So what will you do? We'll take 1, and you cannot put 2 to the left of 1. So you put 2 as the right child of. So you can make 2 as the root. If you do so, then you make 1 as the left child of 2. So there are only 2 possibilities, nothing else. Now you ask yourself that, okay, if the keys are 1, 2, and 3, let us say there are three keys. Then how many distinct binary search trees can I draw? So let us draw 34. 4. Okay. So let us draw some of these. So you have 3 keys, 1, 2, and 3. This 4 keys business will do, but before that, we'll do this later. So let us see with 3 keys only, how many distinct binary search trees can be drawn. So you're saying 4, but let us draw. So one possibility is that we make 1 as the root. So if we make 1 as the root, then 2 has to go to the right of it. 3 has to go to the right of 2 because 3 is larger than 2. So this is one possibility. This is, let us mark it. This is first one. Okay. It's 5. Okay. 5 is the correct answer. So now you can simultaneously work on the real question that how many distinct binary trees are possible if there are 4 distinct keys. So you can start working on that since you've got the answer, but I will draw the rest of them. So let us say this is also possible. So 1 has a child 3 and 3 has a left child. So what, observe that the numbers larger than the root 2 and 3 are to the right subtree of the root. So 1 doesn't have anything on its left subtree. So with 1 as root, we don't have any other options. Now let's look at 2 as the root. So if 2 is the root, then the situation is even simpler. So 1 has to go to the left of it because 1 is smaller than 2, and 3 has to go to the right of 2 because 3 is larger than 2. What are the other possibilities? So let us make 3 as the root. 3 is the root. Both 1 and 2 has to go to the left of it. So let us 1 is here and 2 has to go to the right. The other case is 2 is here and 1 has to go to the left. So 5 possibilities. So the question is, For 4 distinct keys, what shall we do? Maybe the number of distinct binary search trees is quite large. So we'll write a recursion. Okay. So we know that for 3 distinct keys, number of possibilities is 5. Is 5. For 2 distinct keys, number of possibilities is 2. For 1 distinct key, there is only one node. Number of possibilities 1. If there are no keys, then the number of possibilities is again 1 because empty tree. Yes, I think you have calculated it, Ravi, but let's see what is the answer. So now we have 4 distinct keys. So what we know is that we can make 1 as the root, we can make 2 as the root, we can make 3 as the root, and we can make 4 as the root. So now if we have made 1 as the root, then all the elements, or rest of the elements, 2, 3, and 4, have to lie to the right of it. And then how many possibilities? That is, we know that with 3 distinct elements, there are 5 possibilities. So 5 distinct BSTs where 1 is the root. Okay. So if 2 is the root, then 1 has to go to the left of it. And 3 and 4 have to be present in a subtree to the right. So how many distinct subtrees with 2 elements? That we have seen only 2. Okay, so 1 has to go here anyway. There's no choice. So 2 choices here. 2 choices here. Okay. So 2 distinct BSTs. Now let's look at the case when 3 is the root. So 1 and 2 have to lie in the left subtree, and 4 has to lie here anyway. So how many possible subtrees containing 1 and 2? 2 distinct subtrees. It's exactly the case as before. Now, if 4 is the root, then all the rest of the numbers have to lie to the left of it. Now, how many subtrees with 3 distinct keys that we have seen? 5 distinct subtrees, BSTs. 5 distinct BSTs with 4 as a root. So these things are added. So the total number is 5 plus 2 plus 2 plus 5, that is 14. So 14 distinct BSTs. So this is the correct answer. But the question is, if you had a different question, like a question where the number of keys is much larger, it is a 10 or 9, then drawing this, it's a big problem. Okay, it will take a lot of time. So what shall we do? So it turns out that there is a formula, there is a closed form formula. The formula is that if the number of keys is n, I'll just write it as formula. So what is formula? If there are n distinct keys, out of which you want to construct the BST, for constructing a BST, then the number, so this hat means number of distinct BSTs will be equal to 2n Cn, okay, divided by n plus 1. Okay. So let us see if this works for n is equal to 4. So we had the case n is equal to 3 and n is equal to 4. So we'll check both. So for n is equal to 3, we have 6 choose 3 by 4. That is like 6, 5, 4. 4 is already there, 3 into 2. So what happens? 4 cancels. This cancels. So we get 5, which is the answer correctly. Now for n is equal to 4, we have 8 choose 4 by 5. 8, 7, 6, 5 divided by 5 is already there. 4, 3, 2. Some cancellations will happen. 6 and 6 cancelled. 5 and 5 cancelled. 4 divides 8 and gives 2. So this is 2 into 7, 14. So you've got the correct answer. Catalan n by n factorial. Why is that? Catalan number, let's see the formula. What is the formula for Catalan number n? 2n factorial by n plus 1 factorial. Okay, that is also correct. 2n factorial by n plus 1 factorial, that is a Catalan formula. You are saying that thing divided by n factorial. Let's just verify this. So Ravi is saying that another valid thing would be Catalan n. He has written by n factorial. We'll put it here. Catalan n is 2n factorial by n plus 1 factorial. Okay, so that means that all terms. So what is 2n choose n? 2n choose n is 2n factorial by n factorial into n factorial, right? Uh, so I'll keep it n factorial outside. So this is nothing but 2n choose n by n factorial. So this is also correct. Just a second. This is not right. This is not right. Doing fusion will require another n factorial in the denominator. Oh, so this n factorial I have not divided. So that is, this is the Catalan number. This n factorial is here. Now we are in business. Now this part is 2 and choose 2. Or rather 2 and choose n. Now this is equal to this n. This is correct. You're right. Good. So let's move to the next one. We can take a break at this point, or we can move to the next one. We'll just see how difficult or easy the next one is. Wait, what is question number 8? So we have seen the sixth question. We'll go to the seventh one. 5, 6, 7. Okay. So maybe I'll let you read the question and take a break for a few minutes if you like. Oh, this is a direct question. So you either know it or you don't know it. So which of the following algorithm takes non-linear time for sorting? So you have seen in the videos that there are a few algorithms which take linear time for sorting, but modulo certain conditions. So counting sort and radix sort are two such algorithms that work in linear time modulo certain conditions. But quicksort takes at least order n log n time. So cannot work in linear time. Linear means order n. Okay. Let me clarify that. Linear means order n. Non-linear means more than order n. Okay. So order n log n is non-linear. Order n squared is also non-linear. Anything more than n is non-linear. Okay. So since quicksort takes order n log n time, so this is a non-linear time algorithm. All right. Okay. So at this point, I'll go to the next question and take a break, short break. So we are already at the eighth question. So I think we'll be done very soon. The last question is going to be slightly tricky. I'll let you read the question. So yeah, I mean, at this point, it is 6:58. I'll resume after, let us say, 5 minutes. 7:03. Hello. Yeah, we are back again. So we're looking at this question, and the question is, what is the disadvantage of counting sort? So remember, in the counting sort, you have to make an array of size. So you have to make an array of size equal to the size of the maximum element in the input array. So if the input array has maximum element max, so you should have a array of size at least max. Okay. So given this information, what do you think is a disadvantage of counting sort? So in fact, two things. Counting sort has large space complexity because you have to take an auxiliary array whose size is at least uh, max. So let us say we have some elements you want to sort. Let us say you want to sort these elements. Let us say this is 4. Then you have to make an array of size at least 21. So if the max is very large, so space complexity will be high. The second thing is cannot be applied if you have real numbers. So if there is a single answer type question, then probably you will choose D, because in that case you cannot even apply counting sort. Okay, is that fine? Great. So move to the next one. So the penultimate question of today's session. We're closing fast. This is the ninth question. I will let you read it. Consider the following statement. Again, it's a question that you either know or you don't know. To sort n elements, n elements are given to be sorted. Any decision tree must have the height omega log n. So what is the lower bound of the decision tree in a comparison based uh, sorting algorithm? So if it is log n, at least log n, then you will say true. Otherwise, you will say false. Any thoughts? No, no. So minimum height, Ravi is saying that minimum height can be log n for a full binary tree. Okay. So it's a different thing. It's a decision tree. So in a comparison based sorting algorithm, sometimes decision trees are made. So it's the videos if you look. I'll check if I can show you something. So if you Google for decision tree for, let us say, selection sort, then you'll be able to see that decision tree. And it turns out that for comparison based sorting algorithms, the decision tree has height at least n log n. Okay. This will be able to check if you just Google for it. Decision tree for selection sort of any comparison based sorting algorithm. But the question they are saying that must have height log n. So that is also correct, in fact, isn't it? So they're insisting that this lower bound should be at least log n, but the lower bound is even tighter than log n. So I think so you remember the big O and big omega notation, right? So if somebody says that n squared is order n to the power 4, that is correct. Okay. Similarly, uh, if somebody says that n log n is omega log n, that should also be correct. It's the opposite of each other. This I would say true. But this is a tighter bound. Is that right? So the next question. This is the last question, the trickiest of all today's session. And after that, we'll conclude it. I will let you read the question. This is simple, but slightly tricky. Okay, there is something in the previous question. Somebody saying something. Let's take that comment. Senthil Kumar is saying it will be total number of comparison, that is n log n, for comparison based sorting. That is correct. What do you mean n log n? What is the, you didn't say the order. Is it theta n log n, O n log n? Theta. Yeah, so that's what I'm saying. That minimum n log n comparisons are required. If somebody is saying that minimum log n comparisons are required, that is also correct. Even look at it this way. Uh, Suppose I say that I have at least 1,000 rupees. Okay. So minimum I have 1,000 rupees, let us say. So let us say I have at least 1,000 rupees. If I make this statement, and then if somebody makes a second statement based on my statement, that okay, because I have said that I have at least 1,000 rupees, that means that I have at least 100 rupees. That statement is also correct. So if this is true, say if the amount of money I have, let's say X is the amount of money I have. If X is greater than or equal to 1,000, then definitely X is greater than or equal to 100. That's what I'm saying. That is how you should interpret this. Okay. So now we can read this question. The number of ways in which The numbers 1, 2, 3, 4, 5, 6, 7 can be inserted in an empty binary search tree. Remember, a binary search tree is something that respects the binary search tree property. So something that I had drawn before. This property. If there is a node X, then all the elements which are less than X will lie in the left subtree of X, and all the elements which are greater than X will lie in the right subtree of X. So that is the binary search tree property, and this should happen at every node in the binary search tree. Now, the number of ways in which the numbers 1, 2, 3, 4, 5, 6, 7 can be inserted in an empty binary search tree such that the resulting tree has height 6 is. We're asking that in how many ways we can form a binary search tree using these 7 distinct numbers with additional condition. What is the additional condition? That the height of the resulting tree should be 6. And there is a note also. The note says that the height of a tree with single node is 0. So that means if you have a tree like this, one node only, a tree like this, one node only, then its height is 0. So now we have to maintain a height of 6. So that means if we have a height of 6, there are how many levels? So the root node is at height 0. And then so height, we have to come till height 6. So how many height levels are there? 7 height levels are there. So we have 7 elements to insert, only 7 elements. So that means at each height level, we should have exactly one node. Additionally, we should maintain this PST property. So what can the root be? So what are the possible values at the root? Either 1 or 6. So the largest number is 7, remember, not 6. Right. So the largest number is 7. If the smallest number is the root, that is one possibility. So let us say, consider this possibility that the root is 1. Root is 1. So now, since root is 1, the rest of the elements have to be in the right subtree, isn't it? So can one be followed? One have a child which is other than 2. So let us say one has a child 3. Then definitely 2 has to lie here. There is no choice. So because 2 cannot lie to the left of 1. Here 2 cannot lie. This is not possible. So 2 has to lie here. If 3 is a child of 1. So where does 4 lie? So 4 cannot lie anywhere. To the left of 3. So in this space, 4 cannot lie. 4 has to lie here. And as soon as this happens, you see there are 2 nodes at the same height level, that is height equal to 2. That is a problem. Because we have already observed that because of the restrictions At each height level, we have exactly one node. That is because of the restrictions imposed by the question. So this cannot happen. So that means once you have one in the root, you have also fixed its child to be 2. Anything greater than 2 will not work. This has to be 2. And so on. What is the other possibility? The other possibility is 7 is at root. Seven is at root. And all the rest of the elements have to be in the left subtree of 7. So by similar argument, 7 can have only 6 as said. Because if it has 5, then what will happen? 5 will have 2 children. One to its left, one to its right. And that is problematic. Getting confused with level and height. Level and height are same things. So the root is at height 0 or level 0. Okay. So for a node, its height or level is the distance from the root. So the direct child of the root is at distance 1 from the root. So therefore, its height is 1. Now, if we draw this fully, then we have the full picture. Let me also draw this fully. So what is it saying? 2 is the child of 1, 3 is the child of 2, 4 is the child of 3, 5 is the child of 4, 6 is the child of 5, 7 is the child of 6. So on. 7 is the father of the parent of 6, 6 is the parent of 5, 5 is the parent of 4, 4 is the parent of 3, 3 is the parent of 2. There are no other possibilities. So we have to maintain height is equal to 6. We have to maintain. What else can I do? Is there anything we can do? So I think the answer is 2. There are 2 possibilities. But these are the 2 possible uh, binary trees, so rather binary search trees with 7 elements having height 6. But the question is slightly different. Question is how many ways are there in which these numbers can be inserted in an empty BST such that the resulting tree is height 6. So does the order of insertion matter? This is something you should think about. So let us say the order of insertion is 1, 2, 3, 4, 5, 6, 7 in this order. 1 followed by 2. Then we don't have a problem. So first you insert 1 into the empty tree. Then you realize that 2 has to go to the right of 1 and so on, you obtain this. But if the order of insertion is something different, let us say 1 is followed by 3, followed by 2, followed by 4, 5, 6, 7. If that is the case, is there a problem? If that is the case, you have the tree. So you have the empty tree. So let me do one thing where I'll make some space here. Then I will do this here only. So this is the order of insertion I'm saying. Oops. So what has happened is 1 has to insert it, followed by 1 we have 3. Okay. But now you have inserted 3, then you are in trouble. As I have said, that if 3 is becoming direct child of 1, then 2 has to lie here necessarily. And then anything else has to come here. So basically 2 nodes coming in one level. That is not allowed. So basically this is not a valid way of inserting these 7 elements such that a height 6 BST can be formed. So there are only 2 valid ways. This is one valid way. 1, 2, 3, 4, 5, 6, 7, or the reverse order. Other than this, nothing else is valid. So this is, I think the answer is. So I think the answer is 2. If you have anything, any doubts or any suggestions or objections, you can let me know. So do you understand why the answer is 2, in my opinion? Great. This is all I had. If you have any doubts, any questions, you can ask me. I can spend another 5 minutes here. So since we have already finished the 10 questions to be discussed, we have some, okay, there is some question. What is asking, sir, we don't use another number. Us note, sir. I don't understand this sentence. Are you saying that we don't use another number? I don't understand. Are you asking with respect to this question? Swati? Sanjay Kumar, do you have a question? Sanjay Kumar. So unfortunately, I'm not able to understand the question that you're asking, or rather, we are just making a statement. Is it possible for you to rewrite the question? At the end of the tree, can't we write 1 is followed by 2, the height remains 6, right? I'm trying to understand what Manjunath is saying. At the end of the tree. So do you mean which tree? So I am going to point. So are you talking about this tree or this tree? Let us say this is tree number 1, this is tree number 2. 3 left side 1, 1 right side 2. So I'm going to draw it. So you tell me how to draw it. So maybe you're right. We'll just check. So what is the root of your tree, Manjunath? Just tell me the root first. 7 is the root. Okay. So 7's left child. What is it? Continue the tree up to 3. Okay. Do that. Nice. Now this is what you're saying. Ah, this is correct. So you have find a flaw, a bug in the argument. That is correct. So this is also binary search tree as Manjuna is pointing out. Thanks a lot. We can write 1 before 2, can't we? That is the question. We can write 1 before 2. Yes, we can do that. So at each node, the BST property is true. So basically this can happen. So we have to count some more trees. I'm glad that you found it. So the answer is supposed to be 64. That's what NPTEL is saying, but I somehow couldn't observe this. So sorry for that. So the answer is not 2 definitely, but why is it 64? I am not able to tell you immediately, but we can spend some time on it. So I think people are convinced that it is a valid PST, right? So I think we should write a recursion and solve it. So basically what can happen is, like, yes, from this here, you can make 3 as the root and make couple of PSTs with this height. You can make 4 as the root and make couple of PSTs. For example, another PST could be this. Now you make 4 as a root. Now from here, what can you do? So you can make 1, you can make 2, and you can make 3, something like that you can do. Okay, so what it means is the following. The basic structure is going to be same, but on top of this structure, we have to do some calculation. Some more possibilities are arising. So what is a concrete yet neat way of doing this? We'll do it here only. So let me remove this part slightly to the down and then we'll do the calculation here. So the question will be of this form that uh, what is the number of valid BSTs rooted at I. So for I, 1, 2, 3, 4, 5, 6, 7. So this is the question we're going to ask. So what is the meaning of a valid BST? Valid BST means that at each level, there is exactly one node, not more than one node at each level. That is the meaning of a valid BST. And of course, the binary search tree property should be satisfied. That left child or left descendant should be smaller and right descendant should be larger. So let us say that this number we denoted by T of I. Okay. So let us say T of I be that number. It's a function we have defined. Swati has given a possible binary tree. That is also correct. Okay, so let us formalize this. So what is T of 1? That means rooted at 1. No. So we have to have two parameters. Like we have to ask a question like what is the number of valid BSTs rooted at I with so and so children. Okay. Should ask concrete question. What is the number of valid BSTs rooted at I? And containing the numbers, let us say smaller numbers, 1 through I. So what has happened here? Why I'm saying all this? So we wanted to know that rooted at 3, how many are there? Rooted at 1, how many are there? That is one question. The other type of question is what is the number of valid BSTs rooted at I and containing larger than I number. So basically I to 7. So this is question 1. And a similar question would be, maybe there's a simpler way of doing this. Maybe I'm just doing something brute force. If there is a simpler way you can find, you can let me know. I'm doing something. Sounds like brute force. Okay, Ravi is giving one approach. Sequence of ascending followed by sequence of descending and vice versa. Yeah, your pattern from your solutions. Okay. So basically, you are saying that if you traverse the list or the tree height-wise, you're getting either an ascending followed by descending, or in this case, there is ascent, descent followed by ascent. So at some point, but it can again change. That is, can it happen that there is a descent followed by ascent followed by descent again? There is a descending sequence 7 to 4, and then there is ascent. Can it happen that there could be descent followed by ascent followed by descent again? Can that happen? That seems unlikely because if you notice that the difference between a child and its parent is always 1. It's not true. 1 and 3 difference is 2. Yeah, within one ascent or within one descent, that is holding. That is true. So let's try to answer the question the way Ravi is suggesting. So this is one full ascending sequence, 1 to 7. Okay. So count one for this, and we count one for this. So this is the second guy. This is a full descending sequence. Now at any of these points, there could be a change. So potentially there could be a change here, 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 here. So potentially 5 places here, potentially 5 places here. So, right, 5, 5. But more things can happen. So it means that we have found 12 possibilities. Multiple transitions are possible. Transitions are possible. I can see 12 possibilities. And plus 1, 5 plus 5. So maybe okay, so now I can understand this. So multiple transitions are possible, right? So maybe something like this can happen. So 5 is here, let us say. This is correct. The way I was doing was complete way of reading. So this is descent, then there is ascent, then there is descent. This is okay. So basically, you have to ask a question like this: that what is the number of valid PhDs rooted at a given point, I, for example, at 5, and containing the numbers 5 or more. So let us say this is one possibility, okay, for 5. Now, uh, so I don't know how to formalize it, but I can say definitely that there are more numbers. So even if we solve it, this the way to solve this is not by counting, because here we have only 7 numbers. But if the number is very large, let us say 15 or even 20, then we'll be in trouble. We cannot enumerate all the possible height that number is. I think we have to give it a thought, and I'll give it a thought, and I will look at it next time. But thanks a lot to Manjunath for pointing it out. So the answer is not 2. Answer is not 4. It is at least 12. We have to decide whether 16, 64 or 32. Most likely it's 64, but we have to find a general formula for some given thing. Okay. Any questions? So where you can get the recorded sessions is in the YouTube. You can get it in YouTube. I will share the YouTube playlist with you. I'm going to upload it on YouTube sometime the next 2 days. And the other question is, where can we get more questions? You can get more questions in the book. You can refer to the algorithms book, CLRS, that is which is a textbook. Government's book. How do I copy this? Radius. And this is a previous fundamental algorithms. So at this YouTube link, you will be able to see the videos of recorded lectures or problem solving sessions. Okay, so are there any more questions? Okay, then we'll look at this question once again, this 10th question. I'm not able to formalize it today, but I'll give it a thought and we'll look at it again next time. So next week, whether or not there will be a session, I have to decide. So I'm traveling, and we'll let you know whether there's a change in the date. Okay. Okay, then thanks for joining. I'll see you next time.